Okay, please check your attendance on Blackboard. Then, so as you know, so one student put the question about the last level assignment. Yeah. And then, so actually he found an error the providing the single side process of design. So so I sorry. So I fixed the error, and then so as I posted announcement of the effort, right? So you can use the fixed single cycle process of design for this final lecture platform. Okay. So it's a good student, right? Actually, okay, so we have 5 classes left until the end of the semester. Okay, so stay tuned until the end of the semester. Okay, so we are learning about the memory hierarchy, and then so actually in the previous class, so I briefly explained about the cache. So what is cache? What is the cache memory? So I explained that. So you can find the definition of cache here, right? Okay. So the temporary storage space, okay, and then this cache memory is managed by hardware, not software. Okay, so we can just manage it. We can just manage it data movement or data transfer between main memory and register file using memory instructions like load or store instructions. But so we use cache for improving the performance of memory systems, actually the performance of entire computer systems. So it is because the main memory, so so this is the memory hierarchy. Okay, so the main memory is here, and then register file is here. So and then as I explained, the main memory, so for this main memory, we use DRAM or DRAM devices, and then DRAM is slow. DRAM is a slow memory device. So it's faster than SS, the flash memory or hard disk drives, but it's slower than the register file, right? So we have the computer system, the computer processor has cache memories. So you can find the cache here between the register file and the main memory. Also, you can find the default cache memories like the L1. L means the level. It means level. So this is the level 1 cache, level 2 cache, and level 3 cache. Okay. So actually level L1 cache is on the higher level of the cache hierarchy. So, and then at the extent, the L2 is here, and then L3 is here. L3 is usually the lowest cache memory in the processor. Okay. So if you read some CPU specification like the Intel CPU or AMD CPUs, then you can find the cache specifications also, right? L1, L2, L3, and then L3 is the largest cache. Okay, so it means this is the lowest cache, the lowest level cache. And then actually this is called the last level cache. Okay, the last level cache, LLC, last level cache. Okay, so why do you use cache? So as you can see, cache is a temporary storage space, and then the cache is faster than main memory. Also, the size is smaller. Okay, and then that allows fast access to data. Okay, so So actually, we store frequently used data. So it's a frequently used. What does that mean? So we learned about the data locality. It's a temporal locality and spatial locality. So what is locality? The locality means that a certain data, a temporal locality, same data will be reused in the near future. So it is frequently used in the near future. And then spatial locality, so close data, so near data will be will be accessed, will be used and used in the near future. So it means also frequently used in the near future. So we store frequently used data because the cache size is small. It is smaller than the main memory. So we cannot store every data in the cache memory, right? So we just store the smaller size data, and then but we need to store frequently used data, right? Then we can improve the performance. We can improve the performance of memory systems, right? Okay, so let's see the some analogy of cache in real life. Okay, so it's so in this slide you can find the bookshelf here. The bookshelf has many books. Okay, and then let us also that you are preparing for the computer architecture exam. So which means that you need to read a textbook, right? So, but there are many books here. Okay, but when we study for some courses, then we just focus fewer number of books, right? We don't need to search this entire books, right? We just focus on smaller number of books when we study some subject or some courses for the final exam. So actually, so as you can see, the bookshelf is far from your desk, right? So it means that if I want to study with this book, right? This book and then this book and this book 1, 2, 3. But if these books are in the bookshelf, and then actually we need to pick up the target books, book number 1 from the bookshelf, and then we need to move to the desk. We will leave the books, right? And let us also that we require another books, book number 2. And what should we do? Stand up, then go to the bookshelf, and then pick up the book number 2. But we also replace the books. So which means that we just put the book number 1 to the bookshelf, and then we just pick up the book number 2, and then we read the book number 2. So what's the problem? It will take long time because the bookshelf is far from your desk. So actually we pick book 1 to 3 from the bookshelf, and then we place these books on the desk because we know we will read these books in the near future. And then we just focus on fewer number of books, so smaller number of books, right? We will not read entire books in the bookshelf. So what does that mean? Actually, because of locality, so that is the locality of book locality, the locality of books, we will just read smaller number of books during some time period, right? We will not read entire books. We just focus on reading the smaller number of books. So which means if we replace some books on the desk, then we can save time. Right. That is the analogy of cash in the real life. And then as I mentioned, we can observe data locality, like the book locality. Okay, so which means if a certain data is used, then the same data can be used. Also, the deal data. So this is the certain data accessed by some program, and then the same data can be used in the near future. Okay. Also, the deal data, the closed data. So it's a kind of a book. Okay. So closed data also will be used in the near future. And we can place. So actually, this is kind of a bookshelf. Okay, so the large memory, but it's small. It's slow. Okay, large memory, but it's slow. And then in a certain time period, we will just use a certain data, like the part of data in the main memory. Then we can just store. We can just store this small size data. And then we expect that we will use this data frequently in the near future, a certain period. Then we can store. We can store this data in the cache. Okay. So it's a small memory. It's a small but fast. Because the size of cache is small, and we cannot store entire data in the DRAM, right? But we can just store a part of data in the DRAM, okay, in the cache. And then this data will be frequently accessed. This is the purpose of cache, okay? And then, as I mentioned, the cache is automatically managed by hardware, not software. So actually, you can find the memory instructions like load and store instruction, right? What is load? So if the load instruction is executed, then data is read from the memory, and then data is transferred to the register file. And then if we just execute store instruction, the data is read from the register file, and then data is stored to the main memory, right? So there is no cache. So cache is not accessed by normal instructions, right? So we just use the memory instructions to transfer data between memory and register file. But when the data is transferred by these instructions, the data, the frequently used data will be stored in the cache automatically. So managed by hardware, not software, right? You need to remember that with the data in the cache is managed by hardware, not software. Okay? The cache is here. Cache is here, like this. So we can use the cache like this analogy, like bookshelf, desk, then small number of books. That is the open books. Okay, then when we learned about the process architecture, then we learned that there is memories. There are memories, actually two memories. There are memories in the processor, right? So we learned about the instruction memory. Also, we learned about the data memory, right? And what happened? Why memories are here in the processor? So I explained that. But when the load instruction is executed, the data is transferred from the main memory, and the main memory is a external memory, right? It's a DRAM. What happens? So actually, this instruction memory and then data memory is the L1 cache. So this is the L1 cache. Okay. So, actually, so as I mentioned, this is the level 1 cache. Okay, this is the higher level cache, the highest level cache. Okay, and then so this is the instruction memory. So this is the L1 instruction cache. Okay, so which means that the instruction is temporarily stored in the L1 instruction cache. So actually in chapter 4, we learned that this is the instruction memory, but actually this is an L1 instruction cache. And then obviously this is the L1 data cache. So it's called the D cache because this is the data. So actually in chapter 4, so we learned about the process architecture, but these memories are cache. Then how can we design these cache memories, caches? Then as I mentioned, the cache is the size of cache is small, the smaller than main memory. So which means that we need to decide what data is held in the cache. Right. So actually the main memory has the every data, the main memory, but the size of cache is smaller than the main memory. But so the load instruction is executed, then so we just transport this data in the main memory to the register file. But if the cache is the temporary storage, so which means that the request data can be also found in the cache. So like this analogy, so we want to find a book number 3. Then we can find this book number 3 in the bookshelf or on the desk. There are two cases. It's the same for the cache. So the request data can be found in the cache or found in the main memory. Then we need to decide which data will be stored in the cache. Then as I mentioned, this is decided by hardware automatically, but the hardware needs to decide. Which data will be stored in the cache. Okay, so we need to decide. And the second, how is data found? So think like this. So I explained that the request data can be found in the main memory or found in the cache. Then we need to know the request data in the cache or main memory. Then how can we distinguish? How can we know? How can we identify the data in the cache is the request data or not? How? So question is that how can we identify the required data? Using address. Right. So actually in the program we use our variable names like A or B. So but actually its name is translated into the address like 0 blah blah blah, 0 blah blah blah. Okay. So we can identify data using addresses. So at this analogy, I mentioned book number 3. So which means that we can identify the book with the book number. So that is the address of a data. So which means, we can identify data using an address. So which means that, there are many books like the book number 1 to book number 100 in the main memory, right? In the cache, we just store a smaller number of books, right? So which means a book is, there are 2 books in the cache. Then how can you identify? Using the book number, like the book number 10 or book number 25. So when the book is stored in the cache, then which means we need to also store book number, like 10 or 25. Otherwise, you don't know which books are stored in the cache, right? So likewise, we can identify a certain data in the cache or not using addresses, right? Which means, oh, data is here. Then how can you identify? We need to use the address. So which means when the data is stored in the cache, we need to store the addresses of data alongside with the stored data. Okay, so like the phone number. When the book is stored in the cache, we also need to store book number in the cache in order to identify which book is stored. Today, when the data is stored, which means likewise, we need also store address, right? We need to identify which data is in the cache. Okay. And then the third, what data is replaced? Why do we need this? Because the cache size is limited, it's smaller. So for example, oh, there are 2 slots in the cache here, and then we want to store another book, like the book number 30 book number 30. But this cache is already full. There is no empty space in the cache. Then we need out a certain book, one of these books. So we need to decide, okay, what data is replaced, what data will be kicked out from the cache. So this is called the eviction. So eviction. So evict actually is a kick out. Okay, so the meaning of eviction is kick out. Replaced. So when the data is evicted from the cache, then we need to decide which data will be evicted. Then in the empty space, we can store new data. So when the cache is designed, we need to consider these topics. Okay? So which data will be stored, and then how can, so actually we need to store the address along with the data, and then which data will be evicted or replaced. Okay. So this is the kind of cache, the kind of the concept of cache. So and then this is the access. So and then the x and number represent some address. So as I mentioned, the cache is the limited space, but if there is an empty space, there is empty slots or an empty slot on the cache, then we can store the new data in the cache. So it's okay if there are empty slots or empty space, then we can store new data in this empty slots. Okay. But we also need to decide where to store. What does that mean? So cache. Cache is also a kind of memory. Okay. So what does that mean? So in the previous class, we learned about the basic of memory. What is the memory? So you can understand the, here is it. Memory like this, right? Here. Memory array, okay? So, okay, like this. So we can understand the memory like this. What does that mean? So memory has the data space. So it's called memory cells, one data bits or data cells. And then actually the target data slot or data slot is indexed by address. And the cache is the same. Cache is the memory. The data is stored in the cache, which means that, in order to access the cache, we also need to provide address. Okay, so and then but it's not called an address. It is because so actually, if we just code it that is the address of the cache, then you can be confused, right? Because we use address for identifying the data in the main memory, right? So instead of address, we use the terminology index. Okay, so you can also understand the cache structure like the normal memory structure, like the there are several blocks. Okay, and then these blocks are accessed by index. It's actually it's the address of cache, but as I mentioned, this is not called an address because it's called an index. So obviously, if we just give index number 0, then so we can read the data stored in the first cache slot. And then this slot is called a cache entry. Okay, it's an entry. Sometimes it's also called a cache block or line. Okay, but we can understand this is the cache entry. So index number is given, then the corresponding data can be read from the corresponding cache entry. Okay, actually it's memory, right? Then we need to decide when the data is, the cache is located in between the main memory is here, and then register file is here. So actually, when the data is requested from the main memory, then this data is stored in the cache. Okay. Then where to store? So there are many entries. There are several entries in the cache. But we need to decide where to store this data in the cache. Which means that we need to decide the cache index of the target entry. Okay. And how? So there are several ways. Okay. There are several ways, but in this time, so I will explain about the direct mapped cache. Okay, so I mentioned that there are several approaches that decides the cache indexes, but firstly I will explain about the direct map. So direct map means that when I explain how to identify data, how is the data found in the slide, so I mentioned that we also need to store address, right? So address. So which means that it's a load word. So the address is given, and then it's a target target register file. So address is this address, the address of the data. Then so where to store? So the target cache index is determined by the part of bits in the address. So what does that mean? So let us assume that the address is 0x11110010. Okay, and then if we just use the load word instruction, then we load word instruction transfer 4 bytes of data. And then let us assume that the size of a single cache entry is the 4 byte. Okay, so which means that the word data is transferred to the register file, and this word data is also stored in the cache. But where we need to decide the target cache index. So direct map means that we just use the part of this address as the index of cache. So in this example, so we just pick these 2 bits because this is the word data, and then one slot occupies the 4 byte of address. So we just use the 2 bit from the address of the data. Okay? Then it becomes the index. Okay? It becomes the so this becomes the index of cache, and then which means that this data is stored in the index number 0. So location, the target cache index is determined by address. So this is the direct map cache. But the cache size is smaller than the size of main memory. So which means that we cannot use entire address. So we can use just the part of address. So this is the example. So this is the word address. Okay, this is the word address, and then cache has 8 entries, right? So cache has 8 entries. So you can find the cache index here, index number 0 to index number 7, right? Also, this is the main memory. Okay, you can find the word address here. So this is the word address of the main memory. But you can find that the index bit, so cache has the 3 indexed bits because the cache has 8 entries. Then the memory has the 5 address bits. Okay, so which means that the main memory is the 32 words. Okay, that's just so example. So very unrealistic example, but if so, actually for this example, we use the lower 3 bit as the cache index. Okay, because I mentioned that we use 3 bits because cache index has the 3 bits because there are 8 slots or 8 entries, and then we decide, we use this lower 3 bits as the index of cache. Okay, so what does that mean? We just read data using the word address 0x00001. Okay, then what are lower 3 bits? Is a lower 3 bits 001. Then 001 becomes the cache index 001. Okay, so which means that this data is stored in the cache index 1 of this cache. Okay, also 01001 is also stored in the only this entry, only this cache entry, the same. Okay. So direct mapped cache means that using the lower bit of the main memory address, we use this lower bit as the cache index. Okay. So what is the so which means this is the address 00001, and then we use this lower 3 bits as the index of cache. Okay, so which means that if a certain data is in the index number 001, so which means that we can know the lower 3 bits of the address, right? And also I mentioned that we need to store the address of data in order to identify this data, but we can use the index as the part of we can use the part of address as the index. So which means that we don't need to store this data, okay, using among address bits. But we need to store remaining address bits. Right? We need to identify. So it means that we need to know the address of stored data. We don't need to store this lower bit because it's the same to the index of cache. But we need to store remaining bits. Okay, do you understand? So these remaining bits are called a tag. Why is this called a tag? So we use tag to identify. So we use tag to identify a certain data, right? From many data, so many data. So, and then actually, in order to identify data, we require additional address bits like 00, and then this 00 is also stored in the cache. So this data is this address bits are called a tag in the cache. So which means as I mentioned, we don't need to store these low bits because we use these low bits as the index of cache. But we need to store remaining bits. Then which means that we need to, when the data is stored in the cache, the tag information is also stored in the cache. Okay. And then also we need to store the flag. So it's kind of some control bit. Okay, so which means that we need to distinguish it if the data, the stored data is valid or not. So which means that we require valid bit, right? So cache also needs to store flag or is control bit. These control bits are called flags. So along with the data, we need to store tag and flags. Okay, like it's valid bit, and then it's tag, and then it's data. Okay, so this information is stored in the cache entry. Okay, let's see the example. So this slide shows an example of cache. So you can find there are 8 entries in this cache. So it means that we have this cache as the 3 index bits from 0 to 7, right? Because there are 8 entries. 8 entries, right? And then we will store the data in this cache. So if we see each entry, so you can find the index number is here. So this is just the index. So there it's not, this index is not stored in the cache. So you can find the valid bit. This is the flag. And then you can find the tag space. Tag field here, and then data field. Okay. And then, so let us see that, so which means that the data is stored in this data field. And then let us see that the size of this data is a word. It's one word. Okay. So 4 byte. And this is the direct mapped cache. So which means that the part of address B is used as the index of cache. And then this is the initial state. The initial state means that when the computer is powered, is turned off, and then the computer is powered up, then this is the initial state of the cache. Okay. So what does that mean? Initially, the cache does not have any data, right? You can find the n. So which means that all cache entries are invariant. Okay, so this cache is empty. There is no data in the cache. So the tags are all zeros, then data are all zeros. Okay, so all cache entries are invariant initially. And then this is the word address. So let us assume that this data is requested from main memory. So like the load word instruction. So a processor executes a load word instruction, and then data is requested from the main memory. And then in this table, you can find the word address here, and then this is the binary address of this word address, right? The word address is the 10110. Okay. So what is the cache index? So I mentioned that we use lower 3 bits. Lower 3 bits as the cache index for this cache, right? So here. So firstly, the load instruction is executed, then the processor check cache. Okay, we log. So when the data is requested, then the processor firstly checks the cache if the data exists in the cache or not. Okay, so processor checked cache, but the processor checked the cache, but the slot is invariant, which means, oh, in this cache entry, there is no valid data. So which means the request data is not found. Is it? Miss. This is miss. Okay. The data is checked. The request data is checked in the cache, but if the data is not found, then this is miss. Okay. Then the data is requested to main memory. So, the main memory is slow, so it will take longer cycles. Okay. So data is transferred to the cache. Okay, from main memory to the cache. Okay. Then this data is stored in the cache. Right. You can find the data here. The new data allocated to the cache. And then we need to store tag. not identify this data. So what is tag? Tag is 10. 110 is the target cache index 110. Then what we need to also store the remaining bits tag here is 10. And then if because the valid data is stored in the cache, then the flag becomes 1. So it's a value, right? Another request is given, the word address 26. So it's a 11010. Okay. So as I mentioned, these 3 bits are cache index, right? Cache index. But you know, this is invalid, right? So it's also miss. You understand? Miss. So request is given to the main memory. And then the data is stored in the data is transferred from the main memory, and then this transferred data is stored in the cache. But where? That's 101. So tag is stored, the data is stored, and then the flag is changed to valid. And then after that, the word address 22, word address 26. So, and then as you can see, these requests, the word address 22 is requested before. Also, the word address 26 was requested before. So, 22 is requested to the cache. Okay, so this request is given to the cache. Oh, the binary address is 10110. So because the cache index is 110, then we need to check the 110, the cache entry indexed by 110. So this cache entry has valid data. So there is a certain data, is a valid data. Then we need to check if this stored data is it's the same to the request data or not. Okay, how? So this is the cache index. You can just compare the others. So this is 10. Oh, it's the same to the tag stored in the cache, which means that the request data is found in the cache. You understand? So we access cache with the index part of the address, and then we just compare the tag in the address with the tag stored in the cache. If is tag and then the tag in the address is the same, which means that request data is in the cache. Okay, it's hit. Okay, then this data is given to the processor. Okay, do you understand? So what is the benefit? The benefit is that I mentioned that the test is very fast. So if you pick the data will be provided to the processor very quickly. Okay, because cache is fast. 26 is the same. Cache index is 10010. It's a valid. Let's compare the tag. Tag is 11. It's the same. It's hit. Then data is provided to the processor. Okay. So 16, 3, 16. So 0, 0, 0, 1, 0, 0. So as you can see, this hit. Okay. So all the sequence is like this. So it's a miss hit. So you can check by yourself. Then it replace case. Why? The word address 18 is requested from the processor, the word order instruction. Oh, let's check the cache. So this is as a binary address, this is the 10010. Oh, cache index is 010. Oh, cache index is here. 010 is here, and then it's valid, right? But as you can see, 1101 is here, it's valid, but tag is 11. So, and then the tag of the request data is 10. So what's the problem? Even though the cache index is the same, and then the target cache as the assorted data, as valid data, but tag is different. So in the cache, the tag is the 11th, but the tag of the request data is 10. It's different. Other than that, in the target entry of the cache, there is a valid data, but this data is different from the request data because address is different, which means that the tag is different. So it's miss because tag is not the same. Tag is different. Okay. So in this case, we need to request data to the main memory because the request data is not found in the cache. Okay. Then the data is transferred to the cache. Okay. So this is the new data. This data needs to be stored in the cache index 010, right? Because this is the index address. Okay. So the old data is evicted from the cache, right? Because new data needs to be stored in the cache. This is entry, okay? But there is already old data. This old data needs to be replaced. Okay, so the cache size is limited. We cannot store old data. So the old data needs to be replaced. So old data is evicted from the cache. So then the tag is updated with the new tag 10, and then new data is stored in the cache. Okay. So I explain the operation of cache with examples. Okay. So firstly, the cache is in the initial state, the cache does not have any valid data. All entries are invalid. And then when the target entry is empty, so which means that a target entry is invalid, and if the data is the request is given to the cache, then the new data is stored in the cache. And then this data can be stored in the empty cache entry, right? So the target index. Okay? And then based on the result of the test, then there can be two possible results, hit and miss. So it means that the data is found in the cache, then this means that the request data is not found in the cache. Okay. Also, the data can be replaced. It is because so there is a valid data in the cache, but this data is different from the request data. Then the old data needs to be evicted from the cache, and then the new data is allocated to the cache. Okay. So this slide shows the figure of cache, the structure of cache. Okay, and then Okay. So, and then we can access cache using the address, okay? Like the load word x1 and then 0 x2. So, and then we learned that in the chapter 4, we can calculate the address using this part, okay? So this is the address. And then we are learning about the 32-bit computer system. So address is the 32-bit, okay? And then I mentioned that the part of the address, so we can use the lower part of this address as the cache index. Okay. So in this example, so we use the 10 bits of address as the cache index. So which means this cache has 2 to the power of 10 entries. Right, because we use so this 10 bits of address as the index of cache. Okay. So which means there are 2 to the power of 10, which is the 1024 entries in the cache. But you can find the byte offset here. What does that mean? This byte offset represents the size of a single cache entry. Okay, so this is the address. So it means that this is the byte address. But a single cache entry can store multiple bytes. Right. So for example, when we execute the load word instruction, then the load word instruction actually transfer 4 bytes of data. Actually, we frequently use the large size data, right? So actually integer type is also 4 bytes. Okay. So this example shows that a single cache entry stores the 4 bytes of data. Okay, so which means that the LSB2 bits are used as the byte offset. Okay. After that, so which means that so this represents the size of a single cache entry. And then after that, the lower part of the address bit, we can use these bits as the cache index. Okay. Then the remaining bits, bit number 31 to 12, we can use this bit as the tag. Okay. So and if you see the single cache entry, as you can see, single cache entry towards the cache flag, the valid bit, then tag, okay, then data. Okay. So using the index, we just access the target cache entry, okay, with the index, and then we check the valid bit and compare the tag using the tag part of the address. You can distinguish if the cache has the cache data or not. Okay. Then if the tag is the same and then it's valid, then we can access the data from the cache. Okay. Data is program. So this is the structure of the cache, and then this figure shows how the address of data is used for the tag and index of cache. Okay. So actually it's the same to this example. Okay. In this example, a single cache block has 4 bytes of data, but we can increase the size of a single cache entry. Okay. So, and so we can calculate the size of cash here. How? Oh, a size of a single cash entry is the 4 byte, right? And then there are 1024 entries. So it's the 4 kilobyte, right? You understand? The cache size is the 4 kilobyte. So, but we may use the larger cache. Larger block. What does it mean? In this example, the size of a single cache entry is not over. But we can set the size of a single cache entry as the larger size, like the 8 byte or 16 byte. It's also possible. Okay. So what is different? The large block size. So, okay. So in this example, there are 1024 blocks. Then a single block size is the 4 byte. So which means that I mentioned that the cache size is the 4 kilobyte. Okay. So if the cache size is the same, like the 4 kilobyte, then if we increase the size of a single block as the 16 byte, which means the byte offset becomes 4 bits from pin number 3 down to 0. We can use the 3 down to 0 as the byte offset. So this is which means that the size of a single cache entry is increased. But if the size of cache is the same as the 4 kilobyte, then how many entries? So 4 kilobyte, and then a single entry size is the 16 byte, then increased. How many entries? It's 256 entries. What does it mean? If so we can use the larger block size of the cache. Okay? But if the cache size is the same, then the number of entries is to be decreased. Okay. Then what is the benefit of larger block size? And what is the different operation of this larger block size? So in this example, I mentioned that when the data, the request to the cache is missed, then the cache, so the request data is given to the main memory, and then the target cache block is filled with the data from the main memory, right? Which means, if the bit is observed in the cache, this is encountered in the cache, then the cache block requests the data of this block to the main memory, and then the data occupies the target cache block, which means if the block size is larger, then cache requests the more data to the main memory. Okay, so which means that when the bit is encountered in this cache, then when the bit is encountered, then this cache requests the 4 bytes of data. But if we use the 16 bytes of block in the cache, then if the cache miss happens, then 16 bytes of data is requested to the main memory. Okay, so this is different. Okay, and then so which means that the cache penalty, miss penalty is increased because the more data is to be transferred from the main memory. So this penalty is increased. But if we use the large block cache, then we can exploit the spatial locality. Okay. So large block may, so it's not always, but it's may reduce mislead because spatial locality. Okay? The problem is that if the cache size is the same, and if we use the large block, then the number of entries, number of cache entries is decreased. So we cannot store the same data. The data size is the same, but the cache is, we cannot store just pure blocks. Okay. Also, the miss penalty is increased. Okay. Because when the cache miss is encountered, then more data is transferred from the main memory. Okay. So actually, in the chapter 4, we assume that actually the weakest data is always found in the data memory or instruction memory, right? So we do not consider any misses. Okay, but so in this time, so I mentioned that actually those memories are level 1 cache. Level 1 cache is other than mean, which means the data can be found or data is not found in the level 1 instruction cache or level 1 data cache. Okay, right. So we assume that when the latency, so actually the data memory takes only one cycle, right? In chapter 4, and also instruction memory takes only one cycle. It's the hit case. The data is found in the cache. So which means that we need to also consider the miss cases or miss case in L1 instruction cache or L1 data cache. So what will happen? If the cache miss is encountered, I mentioned that the data needs to be transferred from the main memory, and it will take longer cycles. It will take long time. So think like this. Oh, we access the level 1 instruction cache, but cache miss happens. It's cache miss. So which means that instruction cannot be fetched from the instruction cache. Which means the instruction needs to be read from the main memory. So what does that mean? Instruction is not fetched, so the processor needs to wait until this data is transferred from the main memory. So pipeline is stored. Data cache is the same. So load word executed, and then the load word access the data cache. But cache miss happens. So then load word needs to stay until the data is transferred from the main memory. So in the pipeline, so it's a memory stage and then execution stage, and then load word is here, but a cache miss is encountered. So load word needs to be stay in the memory stage. Then all pipelines are stored, right? So because the load word is here, then the following instructions cannot be executed. Okay, it stores in the pipeline. So actually, it's stored until the data is transferred to the data cache. Okay. So actually, when on cache means then pipeline are stored. So that's why the cache performance is very, very critical for the performance of a computer system of processor. Okay. Okay, so until now, so we just okay. So until now, so we just discussed how the cache works in the mid register actually. So I just mentioned the load work, the load will be created by a processor, then cache is a big something like that. But we also need to consider the store instruction. So it's a right operation of cache. But we don't have time. So I will explain about the right operation of the cache in the next class. So just try to understand how the data is located. Okay, it's very important. Okay. Thank you for attention. We see you in the next class.